Okay, perimeter 1.16 perimeter and area. Um, the explore section gives us uh, two examples here. They want us to find have an area of 48 square inches. So in other words, they want us to draw two triangles, or I'm sorry, rectangles, different rectangles that have an area um, of 48 square inches. Or 48 square inches. Okay, now remember, area of a rectangle is length times width. Okay, so just two examples. If I have a rectangle that's 6 inches by 8 inches, 6 times 8 is 48 square inches. The other rectangle, now that we want different measurements, I'm going to do 12 inches by 4 inches. 4 times 12, 48 square inches. So two different rectangles that have 48 square inches. Now it says find the perimeter of each rectangle. Okay. So to find the perimeter, let's remember perimeter is add up all the sides. So we know that these are parallel sides, so this has to be 4 inches. These are parallel sides. That has to be 12. So if I add up all of it, I get 4 plus 12 plus 4 plus 12. Another way to write perimeter is 2 times the length plus 2 times the width. See how we got 2 fours? That gives us 8, and 2 12s gives us 24. So here we have 32. Now this is linear, so it's not inches squared, it's just inches. So difference between area and perimeter. Area you multiply to get the squared inches. Perimeter, you just add all the sides to get the linear inches. Okay. Area and perimeter, again, I'm not going to go all into this, just the way they do this, they break it down into units, and it's exactly what I just explained to you. You guys probably know the difference between area and perimeters, and we'll just leave it at that. We'll use the formulas. Again, we're going to use just formulas for areas of triangles. Area of a triangle is 1/2 base times height, or length times width, or base times height divided by 2. It's area of a triangle. The perimeter of, I don't know if you can see this too well. The perimeter here of this odd shape polygon, well, what you have to do is just follow the definition, add up all the sides. And this is on a grid, just like a Cartesian grid or a graph. So this side is 1, 2, 3, 4. Here is 1, 1, 2, 1. This one's a 1. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2. 1. 1, 2. 1, 2, 3. And then this one's 1, 2, 3, 4, 5, 6, 7, 8, 9. And you add all these up. 13, 14, 16, 18, 23, 26, 28, 30, 31, 34 inches, or units, because they don't tell us what it is. Now this one is what we call a composite figure. Because we call it a composite because we're going to break this down into two shapes that we easily know the formulas for. We're actually going to break this down into this could be a square, but I'll call it a rectangle until we know for sure, and a triangle. Okay. Now the perimeter, for the perimeter, we're just going to, for the polygon perimeter, we're just going to add up all the sides again. Let's see, 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm going to hold off on these sides. I'm going to figure the area first, see if there's not an easier way to figure out what the length of these sides. Okay. Areas. This is definitely a square. So this is going to be 6 times 6. For area of the square here, 36 squared units. And for the area of the triangle, remember, area for a triangle is 1/2 base times height. Well, the base here is, if I look at this as this triangle this way, the base here is 6. My height, 1, 2, 3, 4. So my height is 4. So the area here, 1/2, 4 times 6, 1/2, 24, and half of 24 is 12 squared units. Okay, so the area for the whole odd-shaped polygon here, for the entire polygon, is going to be my 12 squared units plus my 36 squared units, and that gives me 48 squared units area. Perimeter. Let's get back to our perimeter here. Well, I don't know the lengths of these, but I can make a right triangle. Okay. Again, here's our 4 units for the height, and it makes a right angle here. I know this is 4. I know it splits it here for 3, and I can use a Pythagorean theorem to find out what the hypotenuse is. So the square root, let's see, I'll do it over here. Square root of, well, a squared plus b squared equals c squared, where c is the hypotenuse. So I'm not, I'll do this, skipping too many steps. So 4 squared plus 3 squared, and we're trying to find the length of the hypotenuse, equals c squared. 4 squared, 16. 3 squared is 9, equals c squared. So 25 equals c squared. Have to get rid of the square. So I'm going to take the square root of both sides. Cancels out the squared. I don't have to worry about the negative because I'm dealing with distance. So I only want the positive 5. This is 5. The hypotenuse equals 5. And these are the same lengths. This one's 5. So the perimeter of my odd-shaped polygon is 5, plus 6 is 11, plus 6 is 17, plus 6 is 23, plus 5 is 28 linear units. So that's perimeter and area. Now let's talk a little bit about similarity. Okay, similarity. When two figures are similar, they have the same shape, but not necessarily the same size. The ratios of their corresponding sides are always the same. Okay. Corresponding sides are in the same relative locations when the objects are orientated in the same way. In other words, they match up. Okay, the following trapezoids are similar, although it's easier to see when the orientations are the same. So sometimes you may want to redraw these images to make them look the same. Now, we're talking about ratios and proportions here. So you're going to have to do some figuring. So 12, this side, we make a ratio of 12. This is the same side in the smaller trapezoid. So that makes our first ratio, 12:6, has to equal this ratio, which is 10/5, has to equal this ratio, 24:12, and that has to equal this ratio, 10/5, which is the same. And they all equal 2/1. You have to simplify every one of those ratios to determine if they're similar. Okay. Triangles shown below look similar because they have the same shape. To verify this, we need to check that the corresponding sides are proportional, that they have to be oriented in the same way. So if I'm looking at this, here's my height coming off that right angle, so that's going to match up with this side of the large triangle. The base is going to match up with this base, and it looks like a right triangle. So this hypotenuse looking side has to match up with that one. So 12 to 54, or they went 54 to 12, has to match up with 22, has to equal 22.5 to 5, and that has to equal 58.5 to 13. What they do here is they take the 54, now they're using colon, I'm going to use fractions. 50, I should use red. 54 to 12, reduce it, and I get 4.5 over 1. Let's see if we do the next side. 22.5 to 5, and that also equals 4.5 to 1. And the last one, 58.5 makes a ratio with a 13, and again, that equals 4.51. We're going to do the same thing with these triangles. Let's see. This one, if you can envision it, spin it around, and it looks like it's a similar triangle. In other words, this side is going to match up with this side. This side matches up with this side. And this side is going to match up with this side. Okay, let's check the ratios. You could go either way. 5.7, 5.7 to 3. Put that in the calculator because you can only compare them when they're reduced. 5.7 divided by 3 gives me 1.9 over 1. Let's see. They want us to find the remaining lengths. So let's see. We did the larger one. We don't know what this is. So we have x over 5 has to equal 1.9 over 1. Cross multiply. X equals 5 times 1.9. 9.5. So this is 9.5 inches. And then the last side, we'll call this one y. So y over 6 has to equal 1.9 over 1. Cross multiply. See, 6 times 1.9. So y is going to equal 11.4 inches. Okay. So that's how you find missing sides, if we're given the fact that they're similar. Okay, figures with the same shape but not necessarily same size are similar. If figures are the same shape and size, they are congruent. Okay, look at the following sequence of figures called their Sierpinski triangles. All the included triangles of every size are equilateral, which means all the sides are the same length and all of the angles are the same length. Notice how each triangle is formed from the previous triangle. Each shaded is split evenly into 4 triangles. Process continues until now. One interesting about the cell center. Assume the first figure has an area of 1 square unit. Then each of the triangles in the second figure has an area of 1/4. Since the shaded area in the second figure is composed of 3 of these triangles, it's the area 3/4. That makes sense because we have the first one is 1. It's split into 4 triangles, of which 3 of those are shaded. That's where we get to 3/4. Repeat the process to find the shaded area in the third figure, fourth figure, and so on. So, okay, the first one, we had that 1 square unit. Second one, we had 3, it was split into 4 triangles. So that means that we ended up with an area, a shaded triangle is 3/4. And then 3 in figure 3, we took these 3 triangles and split it up into 4. So each one of these 3/4 ended up to be, well, 1, 2, 3. Okay, so let's think about this. We had 1 square unit, and we split it up into 3. 3 of the 4 came out shaded. So we have our 3/4. And we're actually going to split that 3/4 up, and we're going to use, for the shaded area, we're going to take 3/4 of that. We're just going to multiply this by another 3/4. Gives us 9/16 for a total area when we split those up. So we're just going to multiply here by the 3/4. By the way, we just did this in the last unit. We're actually getting a geometric sequence here, right? So 9/16 times 3/4 gives us 27 4/64 of the shaded, and then we keep doing that. I'm going to start using a calculator now. 27 divided by 64 times 3/4. Math, enter, enter. 81,256. And I'm going to multiply that by 3/4. Math, enter, enter. And my last one is 243 over 1024. If more figures are produced following the same pattern, what will the shaded area be in the nth figure? Consider, okay, so remember the formula for geometric sequence is a to the n equals our first term times the ratio to the n minus 1. Okay, so what will it be in the nth figure? Well, let's go ahead and plug in what we know. See, a to the n equals our first one is 1 times our common ratio, which is 3/4 to the n minus 1. Consider the pattern in the shading areas in the table. What kind of sequence do they form? We already said geometric. Confirm using results in the table that the shaded area does get smaller as more figures are produced as the same pattern. So let's try 6. Let's use n equals 6. So for the 6th term, I have a 1 times 3/4 raised to the 6 minus 1 equals 3/4 raised to the 5th. Three-quarters raised to the 5th. Math, enter, enter. And actually, that is the 6th term. This nth term, that's what we got. So we just actually proved it. Checks. Because this was the 6th term. Number 7. Assume the first figure has a perimeter of 3 units. Then each sided triangle in the first figure has a length of 1 unit. So each triangle in the second figure has a length of 1/2 of the total perimeter of 3 halves. Since the shaded area in the second figure is composed of 3 of these triangles, the perimeter of the shaded area is 3 times 3 halves, or 9 halves. So I'm going to take it that this is the 9 halves. So we're multiplying it by 3 halves. So our R here equals 3/2. So if it's a geometric sequence. So if I keep multiplying this out, let's see, 9/2 times 3/2 equals math, enter, oops, 24/7 times 3/2, math, enter, 81/8 times 3/2, math, enter, 240, 243/16. And the nth one, I'm going to put the formula for here. A to the n equals our first term 3 times r, which is 3/2, raised to the n minus 1. More figures are produced following the same pattern. What will the parameter shaded in the nth figure? That's what we got here. Consider the pattern and shade. What kind of sequence do they form? Geometric. This is my nth term pattern. Geometric. Confirm using results, the shaded producing the same pattern. So if we do 5, say my n is 5, I should get 243/16. So fifth term equals 3 times 3/2 to the 5 minus 1 is 4. Plug that into my calculator. Hit math, enter, and I get my 243/16. And it checks. And that's it for 1.16. That should give you enough to do your homework.